NEC Section 250.80 requires metal raceways for equipment conductors to be grounded. There is an exception that allows for a rigid elbow buried 18 inches. This situation involves installing a rigid threaded coupling in a 1/2 inch raceway to transition from polyvinyl chloride, or PVC, to non-metallic flex for a 20 amps 220 volts fractional horsepower motor. The authority having jurisdiction, or ORJ, issued a violation citing the possibility of live metal parts becoming energized and creating a hazard. The argument is that it is highly improbable for the bare copper conductors to make contact with the rigid coupling due to the non-conductive polyvinyl chloride male adapter threads and non-metallic sheath cable, or NMFC, fitting threads extending into the coupling. NEC Section 250.4 A5 allows for the use of non-metallic raceways attached to metal raceways within 18 inches of the point where the conductors enter or leave the equipment. UL 514. B. Conduit, tubing, and fittings for conduit and tubing permits the use of metal couplings with non-metallic raceways, provided that the metal coupling is bonded to the non-metallic raceway. NEMA WC7 Wiring components permits the use of non-metallic raceways in hazardous, classified locations when the raceway contains metal fittings that are bonded together and connected to the equipment ground. Here are some possible resolutions. Firstly, demonstrate to the AHJ that the conductors cannot make contact with the rigid coupling. Secondly, install a metal coupling with a bonding jumper between the coupling and a non-metallic raceway. Thirdly, replace the non-metallic flex with a metal conduit or cable tray. While it may seem improbable that the bare copper conductors would make contact with the rigid coupling, the NEC requires metal raceways for equipment conductors to be grounded. The exception for a bared rigid elbow does not apply. However, there are NEC and industry standards that permit the use of non-metallic raceways with metal fittings, provided that certain conditions are met. By addressing the AHJ concerns with a suitable solution, the violation may be resolved. It is important to thoroughly understand the relevant sections of the NEC and industry standards to ensure compliance and safety. Here's a deeper dive into the code sections and standards mentioned. NEC Section 250.80 specifically addresses the grounding of metal enclosures and raceways for service equipment. It mandates that metal enclosures and raceways containing service conductors must be grounded. The purpose is to provide a low impedance path for fault current, ensuring that overcurrent protective devices operate promptly to clear a fault. This reduces the risk of electrical shock and fire hazards. The exception for a rigid elbow buried 18 inches typically applies to situations where the underground metallic conduit serves as a physical protection for the conductors. The earth surrounding the buried elbow provides a degree of grounding. However, this exception is very specific and does not apply to the transition from PVC to non-metallic flex in the described installation. Now let's look closer at NEC Section 250.4 A5. This section deals with the grounding requirements for alternating current, or AC, systems. Subparagraph 5 specifically addresses the use of equipment grounding conductors. It allows for the use of non-metallic raceways under certain conditions, such as when they are used as short sections to protect conductors entering or leaving equipment. The key is that the non-metallic raceway must be within 18 inches of the equipment, and the equipment grounding conductor must be properly installed and connected. This provision recognizes that in some cases, a short length of non-metallic raceway may be necessary for physical protection or ease of installation without compromising the overall grounding integrity of the system. Now let's look at UL 514. This standard covers conduit, tubing, and fittings for conduit and tubing. It sets the requirements for the construction, performance, and marking of these products. When it comes to metal couplings used with non-metallic raceways, UL 514, it emphasizes the importance of proper bonding. Bonding ensures that the metal coupling is electrically connected to the grounding system, providing a low impedance path for fault current. This is typically achieved by using a bonding jumper or other approved means to connect the metal coupling to the equipment grounding conductor. NEMA WC7 provides standards for wiring components, including raceways and fittings. It addresses the use of non-metallic raceways in hazardous locations. Hazardous locations are areas where flammable gases, vapors, or dust may be present, creating a risk of explosion or fire. In these locations, it is crucial to ensure that all electrical equipment is designed and installed to minimize the risk of ignition. NEMA WC7 permits the use of non-metallic raceways in hazardous locations, provided that certain conditions are met. One of these conditions is that any metal fittings used with the non-metallic raceway must be bonded together and connected to the equipment ground. This ensures that any fault current will be safely conducted to ground, preventing the buildup of static electricity or other potential ignition sources. In the described scenario, several possible resolutions were suggested. The first resolution was to demonstrate to the AHJ that the conductors cannot make contact with the rigid coupling. This could involve a physical demonstration using the actual components installed in the field. By showing that the non-conductive PVC male adaptive threads and NMFC fitting threads effectively isolate the conductors from the metal coupling, it may be possible to convince the AHJ that there is no realistic risk of the metal parts becoming energized. However, it's important to remember that the AHJ has the final say in interpreting and enforcing the NEC, and they may still require additional measures to ensure compliance. The second resolution was to install a metal coupling with a bonding jumper between the coupling and the non-metallic raceway. This would provide a direct electrical connection between the metal coupling and the equipment grounding conductor, ensuring that any fault current would be safely conducted to ground. The bonding jumper should be sized according to the NEC requirements based on the size of the circuit conductors. The third resolution was to replace the non-metallic flicks with a metal conduit or cable tray. This would eliminate the transition from PVC to non-metallic flicks and ensure that the entire raceway system is made of metal. This would simplify the grounding requirements, as the metal conduit or cable tray would provide a continuous ground path. However, this option may be more expensive and time-consuming than the other two resolutions. Ultimately, the best resolution will depend on the specific circumstances of the installation and the preferences of the AHJ. It is important to carefully consider all of the options and to choose a solution that provides the best combination of safety, cost-effectiveness, and compliance with the NEC and other applicable standards. Here are some additional considerations. The type of motor being used can also influence the grounding requirements. For example, if the motor is a critical piece of equipment, such as a fire pump motor, the grounding requirements may be more stringent. The location of the installation can also be a factor. If the installation is in a wet or damp location, or in a hazardous location, additional precautions may be necessary to prevent electrical shock or fire hazards. It is important to consult with a qualified electrical engineer or electrician to ensure that the installation is safe and compliant with all applicable codes and standards. Proper documentation is also essential. Keep detailed records of all materials used, installation methods, and test results. This documentation can be helpful in demonstrating compliance with the NEC and other standards, and can also be useful for troubleshooting any problems that may arise in the future. Grounding and bonding are critical aspects of electrical safety. By understanding the relevant NEC sections and industry standards, and by implementing appropriate grounding and bonding techniques, it is possible to minimize the risk of electrical shock and fire hazards, and to ensure the safe and reliable operation of electrical equipment. Now let's talk more about the bonding jumper. When a metal coupling is used to connect non-metallic raceways, a bonding jumper is often required to ensure electrical continuity. The size of the bonding jumper is determined by NEC Table 250.102, Seat 1, which is based on the size of the ungrounded conductors in the circuit. The bonding jumper must be made of copper or other corrosion-resistant material and must be securely connected to both the metal coupling and the equipment grounding conductor. The connection must be made using approved methods such as listed connectors or exothermic welding. In some cases, it may be necessary to install multiple bonding jumpers to ensure adequate electrical continuity. This is especially true when the metal coupling is long or when the raceway system is subject to vibration or movement. When installing bonding jumpers, it is important to follow the manufacturer's instructions and to use the correct tools and equipment. Improperly installed bonding jumpers can be ineffective and may even create a safety hazard. Let's also discuss the use of metal conduit or cable tray as an alternative to non-metallic flex. Metal conduit and cable tray provide a continuous ground path which simplifies the grounding requirements and eliminates the need for bonding jumpers. However, metal conduit and cable tray can be more expensive and time-consuming to install than non-metallic flex. They may also be more difficult to work with in tight spaces or in areas with obstructions. When using metal conduit or cable tray, it is important to ensure that all connections are properly made and that the system is securely supported. The conduit or cable tray must be grounded in accordance with the NEC requirements using approved grounding methods. In addition to the NEC and UL standards, there are other resources that can provide guidance on grounding and bonding. These include the IEE, the International Electrical Testing Association, or NETA, and various trade organizations. These organizations offer training courses, publications, and other resources that can help electrical professionals stay up to date on the latest grounding and bonding techniques. It's also worth mentioning that grounding and bonding requirements can vary depending on the specific application. For example, the grounding requirements for a healthcare facility may be different from the grounding requirements for an industrial plant. It is important to consult with a qualified electrical engineer or electrician to ensure that the grounding and bonding system is designed and installed to meet the specific needs of the application. Grounding and bonding are not just about safety. They also play a role in the performance and reliability of electrical equipment. A properly grounded and bonded system can help to reduce electrical noise and interference, which can improve the performance of sensitive electronic equipment. It can also help to prevent voltage transients, which can damage electrical equipment and cause downtime. In conclusion, grounding and bonding are complex and multifaceted topics. By understanding the relevant NEC sections, UL standards, and other resources, and by implementing appropriate grounding and bonding techniques, it is possible to minimize the risk of electrical shock and fire hazards, and to ensure the safe, reliable, and efficient operation of electrical equipment. Remember, when in doubt, always consult with a qualified electrical engineer or electrician.